So today our presenter is Dr. Will Dunn from University College London. Will completed his PhD in 2017 at the Mullard Space Science Laboratory. He then moved to the Harvard Smithsonian Center for Astrophysics for 2 years before moving back to UCL on a European Space Agency and UCL Networking Partnership Initiative Fellowship, followed by an Ernest Rutherford Fellowship. Will is now a lecturer at UCL. His primary scientific focus is the study of X-ray emission from planets across the solar system. He also has a keen interest in making science more inclusive, as has been leading the Orbyts Research-with-Schools program since 2016. Both interests we'll hear about today in this two-part seminar, starting with a tour of X-ray emissions from across the solar system. I'll now hand over to Will.
Great, thank you. And thanks so much for the invite and the opportunity to talk today. So yeah, let's full screen this and we'll just get started. So yeah, so the talk will be about 35 minutes on the science and 25 minutes on the inclusivity program, Orbyts. You can see my screen okay, right? Great, okay. So let's kick off. So our two workhorses really of X-ray astronomy for the last 25 years have been Chandra and XMM. There are other fantastic instruments like NuSTAR and NISA and more recently CRISM, but really Chandra and XMM have led the solar system investigations. And so most of my talk today will present data from Chandra or XMM. Chandra is the NASA flagship X-ray instrument. It gives us phenomenal spatial resolution and timing resolution. But the instrument that gave us spectral resolution has had problems since the early 2010s. In contrast, XMM gives us phenomenal spectral resolution, but worse spatial resolution, but much higher sensitivity, so we get more photons with XMM. Chandra, really, you can count the number of photons you see in any given image, and with XMM, that's marginally more challenging. Any images I show today, or spectra, or time series that I show today are pretty much from these two instruments. But the whole talk will be given through the lens of the fact that we're now at this kind of entering, I guess, a golden age of lightweight X-ray instrumentation. It's now possible to fly X-ray images that give you this imaging and spectral and temporal capabilities and weigh up to a few tens of kilos. And so we're entering an era where these are going to give us new scientific findings and they're going to open new scientific opportunities. And so all of the science that I present in the talk will be through the lens of, well, look at this cool new instrumentation. What could we possibly do with it at these planets, basically? And so we'll see the start of this generation really in the coming year with SMILE having its soft X-ray imager, the SXI, which I'll come to in a couple of slides' time, and BepiColombo with mixes, which will be used to study the surface of Mercury. So SMILE will be used to study space weather at Earth and the impact of space weather on Earth, and mixes to study the surface composition of Mercury and also the interaction of plasma with Mercury. So I guess SMILE is very much a missed science instrument and spacecraft, and so the soft X-ray imager on SMILE will be used. Let me just move this. Okay, so the soft X-ray imager on SMILE provides a novel capability. Really, it lets us image the magnetopores via the magnetosheath and the cusps of Earth. And so that really gives you videos of how the solar wind drives changes in the terrestrial magnetosphere. There's also NASA's LEXI instrument, which took data a couple months ago. And so I believe that data is still being reduced at the moment. And so we should get some first results from that. But that only lasted a couple of weeks, where SMILE will last hopefully many years. So how does this work? So it utilizes this process of solar wind charge exchange. So that's where a highly charged ion from the solar wind, for instance, O7+, collides with a neutral. When it collides with a neutral, it steals an electron from that neutral. And if it's sufficiently highly charged, that electron will drop through the energy levels and produce an X-ray photon. And so that X-ray photon lets us image places where this charge exchange happens, places where highly charged ions collide with neutrals. And it also gives us characteristic emission that can both let us probe the ions, and if we had sufficient spatial resolution, would let us probe the neutrals as well. And so SMILE soft X-ray imager is going to do this for the terrestrial magnetosheath. It will take images of the terrestrial magnetosheath through this solar wind charge exchange emission, where highly charged ions from the solar wind build up in the magnetosheath and charge exchange with neutrals from the terrestrial exosphere. You'll also get emission from the cusps, which you can see in these figures down here. where the solar wind pours down the cusp into denser and denser regions of the terrestrial atmosphere. So this process of charge exchange is actually a fundamental and universal process across the cosmos. It's been seen from everything from supernovae to the boundaries of other star systems, to Pluto, which we'll talk about in a bit. So I'll keep coming back to this solar wind charge exchange process and the fact that it gives us this novel capability of imaging and videoing the interaction of the solar wind with a given magnetosphere. First of all, though, let's look at what this does to planets that aren't fortunate enough to have their own magnetospheres. So this image, this blurry blobby image, is probably my favorite image in all of X-ray astronomy. That sounds crazy, but context is important here. So what you can see here is this orange blob is fluorescence lines from Mars. And so they're giving you the indication of where the Martian atmosphere is. This green trail that stretches up and over it and under it is actually this solar wind charge exchange process interacting with the Martian atmosphere. And so what you're seeing is basically the loss of the Martian atmosphere. This is obviously super interesting for habitability reasons. We know that Mars had conditions for a very long time, about 1 billion years, that would have provided roughly the same temperature we have on Earth right now, would have provided long-lasting bodies of water on the surface, and yet the loss of its atmosphere over billions of years has led to at least the surface of Mars no longer being habitable. So this process of the stripping of an atmosphere is really important, and I think it's kind of cool that we can just image this process. We can image the loss of the atmosphere where the solar wind's just tearing the atmosphere off of a planet. So then back to this context of what could you do with SMILE-like instrumentation or BepiColombo-like instrumentation, both built at Leicester, with lots of input from the OU and others. I think it would be really cool to send them to Mars to provide long timescale observations of the loss of the Martian atmosphere, to take images and videos of the Martian atmosphere as CMEs hit the planet, as CIRs hit the planet, just during quiescent solar wind. I think that would be a fascinating case, and if solar system scientists want to leverage exoplanets and funding associated with exoplanets, there's a clear case of the interest in space weather stripping of exoplanet atmospheres, and Mars is really our local analog for that process. This is a diagram showing that this is kind of the sheath of Mars, and you can see here from this schematic, this process where the solar wind's built up in the sheath of Mars, and with the X-rays we're able to image the tearing up of the sheath. This process is also seen at comets, and the same process of the comets losing neutrals to the solar wind is seen across the solar system whenever comets get close enough to our X-ray telescopes, basically, for us to collect enough photons. We can use them to observe comets. And also, you can also then use comets as they're sometimes referred to as solar wind socks, in the sense that they provide you with a remote way of tracking what the solar wind conditions are like in a given place in the heliosphere. And so images of this solar wind charge exchange from comets provide that. And again, if we had sufficient spectral resolution, we'd actually be able to use the solar wind charge exchange signatures to probe the neutral composition of the comets. You can also probe things like the outgassing rate, because your solar wind charge exchange depends on your number of neutrals. And so more neutrals outgassed gives you more charge exchange. You can probe rotation. And actually, there's some cool science that you can do with kind of interstellar comets, where if you want to probe their composition, then you see different types of solar wind charge exchange signatures if they're, for instance, nitrogen-related ices versus water-related ices. And so you could probe the composition of things like the recent interstellar comet that's wandered into our solar system with this process. We also see SWIX emission, solar wind charge exchange emission, from Pluto. So you can do this all the way out through the entire heliosphere. Which raises questions of where else in the heliosphere are there places with thick atmospheres that sometimes wander their way into the solar wind that might be interesting to understand the process of the solar wind stripping those atmospheres, or interesting to probe those atmospheres. And so Titan intermittently ambles out of Saturn's magnetosphere and into the solar wind. And so some sort of soft X-ray instrument like the SMILE instrument, like the MIXES instrument that found its way to Saturn, could do that as probably a bonus science case. It's possibly hard to imagine it being sent there just to do Titan-related atmospheric loss science. There are other moons in the solar system that also wander into the solar wind. Uranus has these two, Titania and Oberon. And so they intermittently amble. Well, Oberon probably lives in the solar wind, while Titania sits probably in the magnetosheath of Uranus, based only on the measurements from Voyager back in '86. But again, you could probably probe the loss of their atmosphere and the solar wind interactions with those places through X-ray observations of them if you were to send an X-ray imager to Uranus. And we'll come back to these moons in a bit because they're an important part of the Uranus story. So within the inner solar system, we know that the soft X-ray imager on SMILE will provide us with hopefully years of phenomenal videos of the solar wind interaction with the terrestrial magnetosphere. But there are plenty of other magnetospheres throughout the solar system that hopefully are interesting to the MIST audience, and give us different natural laboratories to probe plasma physics across the solar system and across the cosmos. And so what could you possibly do with a SMILE-like instrument or a BepiColombo-like instrument in those locations? So let's start off, for instance, with Jupiter. Could you study the Jovian magnetopause through those? And so Ben Leopard, who did his master's at Lancaster with Lee Charest, and started this project there and then finished it off on his PhD in Hong Kong, built a magnetosheath model with Atlas, who was also doing an MSc at Lancaster and is now at Northumbria, built magnetosheath models of Jupiter to probe the resulting SWIX emission from them to see, well, what sort of instrument might you need, and would it be possible with our current generation of instruments to study and to image the magnetopause of Jupiter, where everything is so vast. I mean, the magnetopause of Jupiter stretches 100 Jupiter radii away from the planet in the sunward direction. It's a vast, vast system. And when you have things at that scale, that maybe presents the opportunity, for instance, to image things like Kelvin-Helmholtz instabilities or flux transfer events, because they're just at a much larger scale. But unfortunately, Fen has found that no, at least with the current generation of instruments, and even with many science fiction-y future X-ray instruments, it would be incredibly difficult to image SWIX emission from Jupiter. And the problem here is that the Jovian magnetopause, because the system's just so vast, the Jovian magnetopause just sits too far away from a source of neutrals. So you still get this dense buildup of solar wind in the sheath, but there just isn't a sufficient source of neutrals there to give you a strong enough SWIX emission for current generations of X-ray instruments to collect enough photons from to be able to image this boundary and see what's going on. So no, probably you can't do magnetopause imaging stuff at Jupiter. Maybe you could do cusp type stuff. That would be interesting because we don't really understand the nature of the cusps at Jupiter, where they are, how they vary with time, how that solar wind interaction works. And so that's something that hasn't yet been studied, and I think would be a really interesting thing to study. But there is quite a lot of other stuff going on at Jupiter in terms of the X-ray waveband. And so there's lots of other interesting science that we can do there. The Jovian magnetosphere is a really rich system. It has lots and lots of interesting, very highly energetic processes going on. But if you'll permit me to step slightly off of MIST science for a second, I think probably the most interesting thing you could do with an X-ray instrument in the solar system, full stop, is to use the instrument to study the composition of the surfaces of the icy moons at Jupiter. So what happens here is that the Jovian icy moons, particularly Europa, particularly Io, and to some extent Ganymede, are in very intense radiation belts. We're talking about up to giga-electron volt particles. Consequently, Europa, for instance, is perpetually bombarded with these very highly energetic particles. They're constantly hitting the surface of the moon, and so when they hit the surface of the moon, that produces a process called X-ray fluorescence. And so X-ray fluorescence is where if you nudge an electron from the inner shell of an atom, then another electron will drop down to fill that shell, and when it does so, it will produce a characteristic X-ray line. And so you can use that line to determine what something's made of. This is used across our civilization from identifying whether paintings are fakes to whether jewelry is fake to lots of medical processes to just identifying whether, I don't know, there's arsenic in children's toothpaste and things like that. Really important processes of chemical identification. And that's because it gives you these fingerprint signatures of whatever element you're looking at. They give you these, X-ray fluorescence gives you these characteristic lines that tell you this element is nitrogen, this element is carbon, this element is titanium, this element is iron. And so this process is used, there's a colossal amount of heritage in the solar system, to be honest with, for instance, right back to the 1970s in the Apollo era, X-ray fluorescence instruments were sent to the moon to study what the surface composition of the moon was. To Messenger a couple decades ago, studying the surface of Mercury, and now to this new generation with BepiColombo having this imaging capability to do whole maps of the surface of Mercury to identify the surface composition. So there's plenty of presence of this. And actually, for Jupiter and for the moons at Jupiter, we already have proof of concept, I guess. We've used the Chandra ACIS instrument firstly to get a detection. So Ron Elsner in 2002 produced these images showing that you get detections of Io and Europa in the Jovian system. This is the very first X-ray observation of Jupiter with Chandra. Then subsequent to that, Susan Knowlson, I don't know why this has come out in black, sorry. Susan Knowlson probed the spectrum from these in more detail, detected X-ray emission from Ganymede as well. The problem is you're just so far away, right? At Earth, you're collecting handfuls of photons because the distances are so vast between Jupiter and Earth. But what it does let us do is at least show proof of concept. We get the oxygen K alpha line, exactly what we'd expect from Europa. A very strong oxygen line from all of that water ice that covers the surface. The question is, what are all of the other elements that we actually are going to find it very difficult to detect from Earth because the distances are so vast? So my partial pitch for you here is with these 4 plots, which is if you were to fly a SMILE-like instrument or a BepiColombo-like MIXES instrument to the Jovian system on, for instance, China's Tianwen-4 spacecraft or on NASA's COMPASS spacecraft, and I know the folks at Leicester are busy working on that project at the moment. You would actually get just like staggering numbers of photons, to be honest. A typical flyby that would be anything like the other flybys that have been done by Juno or will be done by JUICE or will be done by Europa Clipper would give you tens of thousands of photons every second. So contextually, in comparison with our observations from Earth orbit, we get about in about 0.1 seconds of data from a flyby with an X-ray instrument, we'd get more photons than we've had in the entire 40-year archive combined. So that would really let you do mapping of the surface composition of these places. That's super important for places like Europa, where you need to know what the salts are in the ocean below to understand the habitability prospects. From a mist plasma physics science perspective, it's really interesting to understand the nature of the interaction between the surrounding plasma and the surface of Europa. And it's this, you kind of have a beautiful degeneracy, really, where you're able to study the science of the particles impacting the surface of Europa, or with the atmosphere of Io, or with Ganymede, or with Callisto, and at the same time you can study the surface composition of those places as well, and you can map it. And so with relatively typical effective area, this is SMILE's effective area, which is 5 times less than, for instance, the MIXES instrument that's on BepiColombo, with a reasonably modest field of view, and with currently possible angular resolution, you would be mapping from a typical flyby distance, you'd be getting about 0.5 kilometer resolution on craters, for instance, on the surface of Callisto, to understand what Callisto provides us with, I guess, a probe of the early solar system. It's a relic from the early solar system. So the elemental composition of it is reflective of the early solar system and its origins. So probing through the craters on Callisto could be really interesting. Similarly, understanding other salts in Europa's oceans, sodium-based or potassium-based, and what might that mean for any potential astrobiology that could exist below the surface, or maybe doesn't exist below the surface. Solving these problems is really only possible with the fingerprint elemental identification that's possible with fluorescence X-ray studies. The amazing infrared instruments that will fly on JUICE and Clipper will give you molecular composition, but there will still be a lot of degeneracies in the resulting spectrum because the spectral resolution just won't be fine enough. And you can break those degeneracies with an X-ray instrument. And so, for instance, distinguishing sodium chloride salts like we have in the seas on Earth versus potassium chloride salts, you would need an X-ray instrument to do that. And I think current generation instruments would be capable. Actually, the only problem for current generation instruments is the fluxes that we'll get in the Jovian system are so much higher than anything we're used to, except looking at the sun. And so we'll need an instrument that can read out that data really, really fast, which is kind of a nice problem to have, that we're going to be swamped in data, and is kind of an uncommon problem for X-ray studies of planets. Right, I'll move on from this pitch. So back to Jupiter itself. So aside from the moons of Jupiter, which produce these fluorescent signatures where the plasma collides with the surface, Jupiter itself produces lots of X-rays. It produces X-rays from its aurora, and it produces X-rays from the atmosphere of the disk itself. These X-rays from the equator, these are typically scattered solar photons. So if the sun has a giant flare, you'll see a giant spike in the X-ray emission from Jupiter's equator where the flare hits it, and you can pull the spectrum from that solar flare. We'll come back to that case in a bit. I'm going to start with the aurora. So Jupiter's X-ray aurora probes two different types of particles. You get a bremsstrahlung continuum emission from electrons. That's shown in this figure here as big green dots. So the fat green dots here are hard X-rays, and they're bremsstrahlung continuum from electrons. The orange here that these are overlaid on top of is a simultaneous Hubble observation of the UV emission. And so you can see these big green dots overlay really nicely with Jupiter's UV main oval, which is from co-rotation enforcement at about 40-ish RJ. And then these little green dots here, these are the soft X-rays from charge exchange. And I think it's been relatively contentious for the field for a while whether these originate in the magnetosphere or whether they're solar wind particles, and whether they're therefore indicative of maybe Jupiter's cusps or something like that. I can skip the slide because I've just said it. So Bryn, I've been really, truly blessed with an exceptional PhD student in Bryn Parry. Bryn's been, when you present a plot like this, it's difficult to summarize the sheer volume of work that's gone into it. So here in this plot, Bryn has reduced and stacked the entire last 7 years, well, a 7-year window of X-ray observations of Jupiter. And here he stacked the northern aurora. And so your blue crosses here are data points from XMM observations from well over a megasecond of observing time of Jupiter's aurora. Actually, sorry, that's not true. Over a megasecond of observing time of Jupiter, which when you just take the windows when the aurora is in view, come out at about 600 kiloseconds of observing time. So tens and tens of hours of observing time, actually hundreds of hours of observing time. This is showing a spectrum. So on the x-axis, we have the energy of the X-ray photons that we collect, and on the y-axis, we have the counts, and the blue crosses are our data points. Then in red is a theoretical model that he's convolved with the instrument response to try to fit the data. In this case, he took just a composition measured from the Juno spacecraft in situ for the ions, and combined that with several other models. So one that accounts for the reflected solar emission from the planet, and one that accounts for also the electron precipitation. And so all of these spectral lines are a theoretical model that you then convolve with the instrument response to get this red line. And you can see it's kind of a beautiful fit. It's actually pretty astonishing how good the fits were, just taking Juno in situ data and saying, okay, what if that is our ratio of different compositions of ions? What would that look like as an X-ray spectrum? And you get something that starts just pretty close to this, and you don't need to do a colossal amount of fitting. Bryn, interrupt me if I'm wrong about this. You don't need to do a colossal amount of extra fitting to get those abundances to fit the spectrum really well. The bottom plot shows the residuals in between the model and the spectral data. What Bryn did find when he was doing this is that he needed the ions to be traveling at thousands of kilometers per second to get a good fit to the spectrum. So that means that you need MeV to tens of MeV ions precipitating at Jupiter to generate this X-ray auroral spectrum. So it's a pretty energetic system. I think, though, his second body of work, which is hopefully submitted to journals in the next few weeks, goes a good chunk of the way to addressing this long-standing question of whether it's solar wind that's precipitating in Jupiter's auroral zone or whether it's magnetospheric plasma. And that's because Bryn finds a pretty, by again stacking the spectrum and doing a very clever analysis at the high energy end, in a region that actually we don't normally associate with solar wind charge exchange. So for anyone on the call who's interested in the solar wind charge exchange and SMILE related science, normally you're looking at this end of the spectrum, right? You're like 0.2 to 1 keV type region. And certainly for the terrestrial magnetosphere, you'll be looking at that. There are still solar wind charge exchange lines and other ion charge exchange lines way up to 10 keV. So again, this is only possible because Bryn reduced megaseconds of observations of Jupiter and then stacked them, and very carefully and rigorously reduced them to get to that point. But we get the sulfur triplet, which is a really characteristic sulfur line and is kind of difficult to dispute. And so this is probably suggesting that the vast majority of the X-ray emission from Jupiter's aurora is magnetospheric in origin for the average observation. And so probably it all originates at Io and then kind of works its way out into the Jovian magnetosphere and then eventually rains down into Jupiter's poles as ion aurora from the outer magnetosphere. And alongside this finding of sulfur, Bryn's also got some at least 3 sigma detections of argon and calcium and silicon, which I don't think have been reported before and are kind of interesting contextually, both for understanding the composition of Io and that material that's in the Jovian magnetosphere, or possibly for understanding how much of the material might be solar wind. But Jupiter's aurora it's not kind of a steady process. These ion precipitations aren't happening as like a steady continuous process. They happen in abrupt flare type emissions, where you get a burst of emission and then you wait a little bit and a burst of emission and then you wait a little bit. And so my top plot here is just showing time series from Jupiter across one of the great advantages of X-ray instruments is that you can observe for 40 hours continuously. For instance, Hubble gives you 40 minutes. You get beautiful UV videos which have lots and lots of photons in them, and you can do phenomenal science with them. The X-rays give you just a completely different science case because you get this 40-hour baseline. You can see how things are changing on Jovian day-to-day timescales. And so here you can see Jupiter's northern aurora rotates out of view, and then it rotates into view, and it rotates out of view, and it rotates into view, and it rotates out of view, and into view, and out of view, and into view, across this 40-hour window. And so during that time, you get changes in the auroral behavior, and you can track things that happen in the magnetosphere to see what's triggering this change in the auroral behavior. And so you can see here that there's lots of pulsations happening. And then here there's like a weird little break in the aurora where Jupiter just decides to switch off for a bit and chill out and then switch back on. And so it's a really rich data set, these hundreds of hours of data that we have in the archive. And we've really so far just kind of paddled in it a bit really and dipped our feet. One of the things that you could see there is these bright pulsations. So here's a video from Chandra, and you can actually see the pulses going off. Here, this is sped up, obviously. This is a 10-hour Jupiter rotation sped up to be a few seconds long. But you can see the pulses going off. What's really bizarre about Jupiter's puzzling X-ray pulsations is that they often have a very characteristic timescale to them. And so, I mean, saying they're like quasi-periodic is borderline untrue because sometimes they're just periodic. And so here, for instance, you get a pulse of emission and then you wait about 10 minutes and then you get another pulse of emission, and then you wait 10 minutes, you get another pulse of emission, you wait 10 minutes, get another pulse of emission, wait 10 minutes, get another pulse of emission, and so on, for as long as it's in view until it rotates out of view. And so there's some strange clockwork-like property in the magnetospheric processes at Jupiter that gives us these very periodic signatures and very periodic flares produced by the planet. And then to contextualize this story within everything I've just said, so what this means is that there's a periodic injection of tens of MeV ions into Jupiter's pole every 10 minutes. Sometimes these pulses happen on 40-minute timescales, sometimes they happen on 8-minute timescales, but there are characteristic timescales on which Jupiter decides it's going to inject ions into the polar region. And so we've been able to probe these in more detail thanks to the Juno spacecraft and thanks to being able to compare X-ray observations with Juno spacecraft data. And what we find is that those same pulsations that we see in the X-rays are shared by the compressional mode waves in Jupiter's outer magnetosphere. And so when the outer magnetosphere pulses with a 20-minute pulsation rate, we see the aurora pulsing with a 20-minute pulsation rate. When these compressional waves switch to, say, 40 minutes in the outer magnetosphere, we see Jupiter's aurora switch to a 40-minute pulsation rate. And what we see is that buried in these compressional waves are EMIC waves, so electromagnetic ion cyclotron waves. These aren't necessarily the ones that you might think are typical in the solar wind or at Earth. They're not proton ones. They're instead charged sulfur and charged oxygen, because Jupiter's magnetosphere is full of sulfur and oxygen from Io. But there's kind of a nice a reassuring physics grounding to this, because these EMIC waves, and Emma Woodfield's done lots of lovely work on this, would scatter the oxygen EMIC waves, for instance, would pitch angle scatter oxygen into Jupiter's auroras. So the fact that the EMIC waves switch on every 10 minutes, for instance, and then we see Jupiter's aurora at the same time pulsing every 10 minutes, gives us a pretty, I think, physically plausible explanation for what's going on here, which would be that when you get an anisotropy in the magnetosphere, that switches on your EMIC waves. The EMIC waves cause the oxygen ions to be pitch angle scattered. The oxygen ions travel along the magnetic field line, and then they rain into the pole of Jupiter and produce an X-ray auroral flare. This is kind of a schematic we did for like an ESA press release for this, where Juno sees the EMIC waves pushing the oxygen and sulfur ions towards the planet, and then we see the X-ray flares a few minutes later produced at the planet with the same characteristic periodicity. And when the periodicity of the EMIC waves changes here, the periodicity of the aurora changes here. So to say they're at least correlated, I think we can at least say they're correlated, and I'd argue that they're correlated because the underlying physics connects the two. How are we doing for time? Okay, but the story doesn't have to end there. There's lots of other wave bands that have pulsations at Jupiter, and so maybe they're connected. In fact, if you rewind 4 decades all the way back to the Voyager era, what you find is that there were quasi-periodic radio bursts seen by Voyager back in 1979, and those quasi-periodic radio bursts were subsequently seen by Ulysses, and then by Galileo and Cassini, and have since then been seen by Juno. And so here are some of these strange quasi-periodic radio bursts. So this is just a plot of the radio emission from Jupiter during a given window. And so you have frequency on the y-axis, time on the x-axis, and electricity SD on the color bar. And so you can see here, I've taken a slice just through these radio waves and just through these pulses that you can see of the radio waves. And then I've taken that slice and I've overlaid it with the X-rays, and what we see is that the X-rays and the radio waves show, I think, a reasonably consistent pulsation and connected simultaneous pulsations between the two bands. So it seems like the X-ray pulses that are produced by precipitating ions, which I'd argue are connected to wave-particle interactions, seem to be coincident with radio waves that are produced probably by MEV electrons just above the pole of the planet. This is more instances. We have quite a few examples of this process going on, where you get radio waves, simultaneous X-rays, and simultaneous compressional waves as well. Sorry, I need to be very careful there. What I don't mean is that the compressional waves are simultaneous with the radio waves and the X-rays, because the compressional waves are measured tens of RJ away from where the aurora is measured. But what we see is that they share a periodicity. So if the compressional waves have a 10-minute periodicity, then the X-rays and the radio waves have a 10-minute periodicity as well. Here's another instance, and again, in this instance, we see the ion and the electron data also shares this periodicity with the X-rays, with the radio waves, and with the EMICs. And so here's just an FFT across the different particle measurements. So this is the electron fluxes pulsing with a 45-minute period, the ions pulsing with a 45-minute period, the compressional mode waves pulsing with a 45-minute period, the X-rays pulsing with a 45-minute period, and the radio waves pulsing with a 45-minute period, all from the same observation at the same time. So it seems like there's an underlying connection between the radio waves, the X-rays, and the particles and the magnetic field. We can also start to explore UV and X-ray observations to see whether the UV and the X-rays are also connected. Previous to 2016, we only had one simultaneous observation. That was the one I showed earlier with the UV emission in orange and the green dots showing the X-rays. Since 2016, we've managed to acquire lots and lots of simultaneous X-ray and UV observations, 14 in fact. And so we can start to explore lots of different structures in those. Here, my little white dots are the X-rays that we see simultaneous with the UV emission that's shown underneath it. So these are only 45-minute windows, so we don't collect a colossal number of X-rays in the 45 minutes. For some of them, you could, if you wanted to, name each of the X-rays. But you can see that there are shared emission regions between the two. This is just a GIF showing videos of the X-ray and the UV together. Again, the white dots here are X-ray photons that Chandra observes, and the color bar in brightness in kilorays is the UV at the same time. And so here, for instance, we see plausibly that the X-rays gather along lots of emission happening kind of in this region. And then we see a big old UV flare go off and the X-rays cluster in that region as well at the same time. Yeah, I have 14 of these. I've spent a lot of time watching them. They're actually just kind of fun to just watch. But we don't have time to do all 14. So the time series here shows the X-ray and the UV together, and you can see that there are shared pulsations. You could also take the change in the UV brightness and plot it against the change in the X-ray photons, and you find that they're correlated, so that when the X-rays change in brightness, the UV changes in brightness. And they seem to share periodicity between the two wave bands at 6 minutes. Because it's only a 40-minute HST observation, we can't really probe 40-minute X-ray periodicity and UV periodicity. We can only look at shorter periods. This bottom plot for anyone who does lots of UV exploration. So here I ran a peak detection algorithm through the time series. I then subtracted my UV peaks from my UV troughs to identify what was going on at the times when they had shared X-ray and UV peaks, to work out where was the shared X-ray UV region. And so we get the active region basically here in red. So this is the location where the X-rays and the UV are correlated. This is a different observation, slightly different morphology. And so what we find is that they're correlated to the dusk active region rather than what would probably be named the noon active region, but may also be partly the dusk active region. So it seems like there's a connection between the X-ray and the UV flares. If the X-rays are driven by emic waves, then maybe there are also wave particle interactions that drive the electron precipitation that produces the UV flares. Plausibly, there are whistlers going on at the same time as the emics, or maybe it's that the emics drive MEV electron precipitation, and that somehow generates enough UV emission. But I think that's probably not plausible. You would probably have to have whistlers triggered at the same time as the emics are triggered. Okay, I need to wrap up in about 5 minutes in order to talk about orbits. So I wanted to just show, so just returning back to Jupiter briefly, here we have the equatorial X-ray emission, and I had a phenomenal master student last year, Sam Baranowska, and she's about to start a PhD with Henrik in Northumbria looking at JWST data. She did a really cool study with Bryn and with some Orbit students that Bryn worked with as well, looking at, let me rewind a bit. So I said earlier that the X-ray emission from Jupiter's equator is produced when solar photons are scattered off the hydrogen emission, off the hydrogen in Jupiter's atmosphere. And so Jupiter's atmosphere basically acts as a mirror for whatever the sun's doing. And so you can take the emission from Jupiter's atmosphere at the equatorial regions and use it to probe the solar corona, for instance, and the temperature of the solar corona. And so we can fit that spectrum, fit the temperature of the solar corona. And because we have lots of observations now spread across a solar cycle, we can measure the solar corona temperature using these observations off of Jupiter. Why is this cool? Because XMM isn't allowed to look at the sun. The sun's way too bright to point XMM at. But XMM is really our workhorse for looking at other stars and understanding the stellar activity of other stars. But because XMM can't look at the sun, it doesn't have that ground truth, or that G-type star that you can anchor all those other observations of of other stars' activity to. So by using the Jovian observations, we provide that solar analog. And so the red dots here are the temperature measured off of Jupiter's equator of the solar corona across the solar cycle. And so you can see it nicely traces the solar cycle. That's reassuring. And you can see that there's a correlation between sunspot number and solar radio flux and the solar corona temperature measured off of Jupiter's atmosphere. So then Sam took this a step further and said, okay, well, what other G-type stars are there out there that host planets? And could we take the solar analog and just use it as additional context for those stars? And so she's plotted here on top of this the data points for lots of exoplanet host stars that are G-type stars that are often described as solar analogs, so that you can see where they might sit relative to solar activity at any given time. I think this is kind of a cool additional piece of information for all of those exoplanet host stars, or at least useful extra context. Okay, I might have to rattle through these last bits. So in the Jovian system, there are lots of other X-ray sources. The radiation belts at Jupiter produce X-ray emissions, and that's through inverse Compton scattering. And so you could study the radiation belts at Jupiter with X-ray instruments. You can also study the Io plasma torus, where Io constantly pumps out material into space that forms kind of a donut around Jupiter, and you can study that in the X-rays as well. I'll skip over inverse Compton. If people are really interested, ask me in a minute. So Saturn also produces X-rays. We see X-rays from Saturn's rings. That's fluorescence again. That's this process that lets us identify the composition. And so we see, for instance, oxygen fluorescence from Saturn's rings because of all the water ice in Saturn's rings. We're yet to see X-ray aurora at Saturn, which is puzzling, but maybe says that there are energy limits that Jupiter exceeds and Saturn doesn't exceed. So coming back to this SMILE case, and my last couple of slides will thread the SMILE case back through, but for the outer magnetosphere, for the outer heliosphere planets, could you study Saturn's magnetopause through SWIX emission? So Patrick Rogan and Dan Naylor again did master's projects with Leisha Ray at Lancaster, and they created models of the magnetosheath of Saturn, models of the neutrals. From particularly important here is that Enceladus is constantly pumping out neutrals. And so Saturn has a very rich neutral environment around it. So where Jupiter had this problem that the magnetopause of Jupiter was just too far away from a dense source of neutrals to be able to provide enough solar wind charge exchange emission, Saturn actually has plenty of neutrals very close to the magnetopause. And so what both Dan and Patrick's independent results showed is that, and to quote the key points from those papers, it's likely to be viable that a SMILE-like instrument could image the Saturn magnetopause and take videos of it and understand the solar wind interaction with Saturn's magnetopause, giving you a very, very different system to Earth to study the solar wind interactions with. They're both doing PhDs now, and it's kind of staggering how productive they are. So yeah, look out for Dan and Patrick. They're doing amazing work. We also see X-rays from Uranus. We've seen them from the planet itself. Again, this is super difficult. Uranus is 18 to 20 AU away from us. By that point, the X-rays are so watered down by the time they reach our X-ray telescopes at Earth that it's really difficult to do very much interesting novel science with the X-ray instruments. If you were to fly an X-ray instrument there, it would be a completely different situation. You'd get thousands of counts per second from Uranus itself, from substantial distances away from the planet. And so, for instance, if your Uranus Orbiter and Probe took an X-ray instrument with it, it would be able to probe the atmospheric composition using fluorescence for Uranus, for instance, probe the ring composition, and maybe most exciting, probe the moon composition for places that could potentially host subsurface oceans. We don't know, and we won't know until the Uranus Orbiter and Probe mission gets there. Again, just to come back to the SMILE case, because we're missed, and this is at the heart of our science. Could you study Uranus's magnetopause through SWIX emission? And here, and I promised that I'd return to Titania and Oberon. Titania and Oberon are super important. The moons orbit very close to Uranus's magnetopause, and so again, much like the Saturn case with Enceladus, they provide you with the neutrals in the magnetopause that would give you a detectable, or may give you a detectable SWIX emission. So Dan's produced a beautiful paper here on the SWIX emission from Uranus's magnetopause. And I kind of love this. I think it's super interesting that basically it really depends on season what you're going to see. And that's because seasonally the moons are going to shift whether they're cutting through the magnetopause or they're kind of face on as you approach it. And so here your nose on approaching, and you'd see a ring of emission because the moons are producing, dropping neutrals into this ring around the magnetopause. And so as the system's squashed or expands out from solar wind compressions, you see changes in the ring. Plausibly, I guess this might let you image things like Kelvin-Helmholtz instabilities as they pass through the ring of neutrals. I don't know. That probably needs a lot more thought. And so there are different advantages to traveling at equinox versus traveling at solstice in terms of the things that you'd be able to do with this ring of emission or kind of line of emission that cuts through. And so I think the jury is probably still out on whether you could use SWIX to study the Uranian magnetopause. The system's super interesting. Uranus is tilted, and so its magnetosphere kind of rolls through the solar system. And that produces lots of weird, interesting interactions with solar wind. The reliance on the moon's neutrals is an interesting constraint that probably needs some careful additional thought. But at least Dan's work shows that it seems that if not with current generation instruments, a level of technology that doesn't seem too far off would let you do this. And you just need more collecting area, basically, in your X-ray telescope. So a quick summary before I shift to orbits. We see X-ray emissions from across the solar system, from solar wind interactions, from the surfaces of bodies, through fluorescence, from radiation belts, from aurora. There's lots of interesting missed science that you can do with X-ray observations of solar system bodies. So Orbit's fundamental goal is to make sure that everyone can feel like there's a place for them in science if they want to be in science. There are huge systemic issues at the moment with certain groups just feeling like there's not a place for them in science, and Orbit seeks to address that. And I feel like it should be a point of pride for the MIST community that we lead this, that so much involvement in this now nationally recognized and multi-award winning program is thanks to MIST scientists and the contributions that you've all made. So I think just a big shout out to the community and all the amazing things you've done with Orbits. So for those of you not familiar with Orbits, what does it do? So it's kind of in the tagline, I guess. We partner researchers with schools. We're very lucky to be supported by all these organizations. So a quick overview that I'm sure many of you are familiar with, the kind of chronic diversity issues that exist in science and the chronic teacher shortages. So schools across the UK at the moment, 1 in 7 of them don't have a physics teacher at all. In those schools, you're more likely to be taught physics by a biology teacher, and that biology teacher probably hasn't done physics since they were 16. They're probably phenomenal science teachers, but the only thing that's ever been shown correlated between teachers and student outcomes is a teacher's subject specialism. And if they dropped physics at 16, then it's unlikely that they have a depth of subject specialism in physics unless they've really attended a lot of physics-related CPD. And so the UK is colossally short of physics teachers. Secondly, the problem, we have just chronic diversity issues. We know that from age 16 onwards in the UK, girls are mostly choosing not to do physics. So only 20% of A-level physics is girls in England. We have very low numbers of Black physics PhD students, for instance. We have problems with kids from low-income backgrounds not even choosing physics in the first place, and then they're 6 times less likely to get an A if they do choose it. And so this is really at the heart of what Orbits tries to address. It hopes that we can give students from groups who currently aren't choosing to do physics just an understanding that there's an option there for them and there's a potential pathway if they did want to pursue it. It's not a sales pitch. It's just that this option exists for you. So how do we do it? We pair up researchers, mostly MIST researchers, with local schools, and they go and visit the local schools and crucially, they work on original research projects with the school students. And the goal is to get the school students to be leading the research projects by about halfway through. This isn't a one-off visit to the school. You don't drop in and then vanish and you're never seen again. You meet with the students about 14 times across the year. And so they really get to know you as a person, and you get to know them. We close the program with a conference at whichever university, so whether that's one in the Midlands that's either at Leicester or Warwick, or one in Northumbria, or one in London at the moment, and hopefully in the future maybe Sheffield, maybe Lancaster. We pay PhD students to do this. We're very conscious that a lot of the time the program resonates with people who might be from those backgrounds, and we really need to not culturally tax those people. It's important that they're paid for their work, and the program does take time. And so this bumps up this year to closer to £23 an hour. And we have an annual training program that supports the researchers to deliver the program. How does Orbyts work to address these needs? We specifically target schools with low numbers of physics teachers. We specifically target schools in areas with lots of disadvantaged students. And we require that every school, at least 50% of the students are pupil premium. So pupil premiums are government criteria. That means that the students are either from low-income backgrounds, or they're in care, or they're refugees, or their parents are in the military. And at least 50% of every group has to be girls, plus gender minorities. Why does it work? It works because we're not requiring the teachers to do extra work. The only physics teachers in these schools are so overworked anyway. They already have to support biology teachers to teach the Doppler effect, for instance. They don't have capacity to do programs like this. And we hear that almost unanimously across our teacher cohort. It works because we pair them with a researcher who does the body of the delivery of the program. But what we hear from the teachers is that it really reignites their passion for science. It really inspires them. It reconnects them with science, and it gives them new curriculum contexts to help them deliver, for instance, things to their year 8s on magnetic fields. They might use the aurora now to do that. We hear that from teachers. That's a direct quote from a teacher. But the key reason it works for the kids, and the key reason it's having this really positive impact, is that they actually just get to know scientists as people. It really breaks this this Einstein curse, where they think that scientists have to have some innate level of intellect that's completely impossible. If you look at, for instance, the Aspire study from the Institute of Education, they follow a cohort of girls through secondary school. Several of those girls say they love science, they love space, and they want to do space more. They get straight A stars at GCSE, and then they don't do it at A level because they're not smart enough. And that's such a ludicrous paradigm that we've created with this idea that scientists have to have this level of intellect that's completely impossible for humans to have. We really have to break that. And so it's, I guess, an awkward truth that when they get to know us as scientists, they realize actually we don't necessarily have that obscene level of intellect, and that's a really positive thing to show them that we're to some extent fallible, and that we are human. We see that dramatically shifts their potential to see themselves as scientists. We also let them do real science. So much of school science is rote learning to go on an exam, and that's because there aren't enough physics teachers to do interesting things. There aren't enough physics teachers to mark interesting exams. So you have to set exams that are rote learn, where you write an equation on the exam or you write a learned definition. That is obviously not why most of us do science, right? We do it because we love creatively solving problems. We love discovering new things about the universe that have never been known before. And those are things that aren't the same as rote learning things. And so giving them that sense of agency and giving them that sense of ownership over the direction that science takes really shifts them from this perspective that science is a body of knowledge that they inherit, to them creating that body of knowledge and them writing the textbooks. And that's a shift. And so we see that does profoundly change uptake after the program. So we've heard from several of our schools that they see 100% increases in girls taking A-level physics if they do Orbyts at GCSE. That's sustained change. I can talk in detail about this if anyone has questions about it. We see that also for kids from low-income backgrounds, that we see these 100% increases in them taking A-level physics or going on to do university STEM subjects after they do an Orbyts project. We've also supported more than 300 school students to author papers. We're heading to about 30 publications that have come out of Orbyts. And that really, I think, is a reflection of the authenticity of the research that's happening in the schools. The fact that you as researchers, it's not you taking time out of your PhD or out of your postdoc or out of your lectureship to go and do outreach. It's you just taking that research to a different context and involving the school students in that. There are a couple very real examples of impacts here, but I'll skip over them. Here's some quotes. I'll stick those up at the end. So how does the program actually work? So we launch in the schools. That first session in the schools is just you getting to know the school students, learn their names, learn something about them, because you're going to be working with them for 14 weeks. And what you don't want is at the end of the program to not even know their names. Then as the program progresses, you introduce them to some background science that they'll need to be exploring whatever data sets they're exploring or using whatever models they're using. Then after 4 or 5 sessions of background science, you give them a workshop or a data set that you know works and you know the answers you're expecting from it. They explore that for a few sessions, and then you give them their own data sets or their own models or their own choice of atoms or electrons or ions to fit to the data, and then they kind of go rogue and you see where they end up. I'll probably do this slide and then I'll wrap up. So it's also important, though, that if you're giving this amount of time to schools, that you also get a lot as a researcher out of it. The symbiosis is really important. What we hear from our researchers is a few things. So the program gives them leadership and management training that just it doesn't exist on PhDs, right? This process of both managing a project that you want them to do, but also managing them as people. Convincing teenagers to do research is sometimes a challenging thing. You have to understand what motivates them and try to drive them to do that. And that's a set of skills that are very valuable in life, I think, but maybe you don't typically get on a PhD, I guess. It's also very real communication training. You'll go in 1 week, you'll say some stuff to some students, and you'll think, yeah, I aced that, they got it. And then you go back the next week and you realize they had no idea what you were talking about. And that process, that very real feedback loop for your communication, is very valuable, and I think feeds directly into, for instance, your conference presentations, your posters, how you deliver things. That's an opportunity that doesn't exist if you just do a one-off outreach session and then you never meet people again. You don't get that feedback loop. You don't get the chance to self-improve. We have teacher trainers who run the training program, and teachers who do the training program. So the pedagogy experience and training is very real and useful for the next generation of lecturers. And I think the data is showing that it's a chance to inspire the next generation and positively change people's lives. Here's just a couple examples of posters from schools from the last year and a half. Yeah, Becky had them doing Martian riverbed stuff, looking at studying composition of Martian riverbeds. We've done quantum computing projects, we've done exoplanet observations, we've done proton therapy, done tons and tons of space plasma projects, launched stuff into space to see what the context is in terms of Martian, the possibility for certain things to be Martian astrobiology analogs. The wonderful group at Northumbria have done tons of work on solar flares, solar activity, magnetospheric waves. The amazing group at Leicester have done tons of SWIC stuff. In fact, like Simona, I don't know if she's on the call right now, but she's done some really cool SWIC studies with her group. And Michaela's done this like space weather studies of the aurora and the impact of space weather, and using data science techniques to probe that. Bow shock studies, plasma studies, modeling of the magnetosphere studies have all been done with school students. I'm going to skip the videos because I'm really aware I'm short on time. So just to summarize, if you'd like to be involved with Orbyts, please get in touch. We are only able to give school students, give teachers these opportunities if we have researchers who are interested in doing it, and we can pay you for your time. I think we've built like a pretty solid body of knowledge and best practice in how to do this, having run 250 of these over the last 10 years. Each of those is a different research project run by a different researcher. And it does seem to have a really positive impact. I'll leave some quotes up after this. And mostly just like, if you'd like to read about the impact, you can check it out here. But mostly, I think this is just a massive thank you to all the MIST PhD students, postdocs, lecturers who've delivered Orbyts projects. And hopefully what you see from the impact report, for instance, is that you've had a massively positive impact on people's lives. And that kids who didn't even know university was a possible option for them have gone on to university now and have taken STEM subjects, for instance. That's not the driver again. If they want to choose STEM subjects, great, but we're not pushing it. But they've gone on to university because they met you and you ran an Orbyts project with them. And that's changed the possibilities in their life. So I'll probably leave it there. Please, please, please get in touch if you're interested in being involved in Orbyts.